When a body is partially or wholly immersed in a fluid, it experiences an upward force known as force of buoyancy or upthrust. Because of this, there is an apparent loss in the weight of the body. According to Archimedes' principle, the upthrust or the apparent loss of weight of a body immersed in a fluid is equal to the weight of the fluid displaced. Let us now verify this principle experimentally. Consider two concentric cylinders. One outer hollow cylinder, A, with one of its ends closed, and another inner solid cylinder, B. The solid cylinder fits exactly into the hollow cylinder. It means that the volume of the solid cylinder B is exactly equal to the inner volume of the hollow cylinder A. Take a physical balance and place the hollow cylinder on the left pan. Now, suspend the solid cylinder from the same left pan. Place an empty beaker beneath the solid cylinder. Balance the beam by placing weights on the right pan. Now, start pouring water into the beaker. As the solid cylinder immerses in water, the balancing beam of the physical balance tilts towards the right pan. Continue to pour water till the solid cylinder is completely immersed in it. The left arm of the balance rises. Take care that the cylinder does not touch the sides or bottom of the beaker. The rising left arm of the balance indicates that the solid cylinder appears to lose weight on being immersed in water. This is because of the upthrust exerted by water on the solid cylinder. Hence, the apparent loss of weight of a body immersed in water is equal to the upthrust acting on it. Now, fill the hollow cylinder completely with water. You can observe that the beam is balanced again. This shows that the weight of the water in the hollow cylinder balances the upthrust acting on the immersed solid cylinder. However, you know that the volume of the solid cylinder is equal to the inner volume of the hollow cylinder. Hence, the volume of water displaced by the solid cylinder when immersed completely in water is equal to the volume of water in the hollow cylinder. Therefore, we can conclude that the upthrust acting or the apparent loss of weight of the solid cylinder completely immersed in water is equal to the weight of the water displaced by it. That means Archimedes' principle is verified. Let's conduct another experiment. Take an empty dry beaker and weigh it using a balance. Let the weight of the dry beaker be M1. Suspend a metallic sphere from a spring balance and find its weight. Let it be W1. Take an overflow jar and fill it with water up to the brim. Place the beaker under the spout and immerse the sphere. Suspend it from the spring balance completely into the water in the overflow jar. The water that overflows is collected in the beaker placed under the spout. The reading in the spring balance now shows a lesser value. That means the apparent weight of the sphere when immersed in water is less than its weight in air. Let the weight of the sphere when immersed in water be W2. The difference between W1 and W2 is the apparent loss of weight of the sphere when immersed in water. The apparent loss in the weight of the sphere immersed in water is due to the upthrust acting on it when immersed in water. Therefore, The upthrust acting on the sphere when immersed in water is equal to the apparent loss of its weight. This is equal to W1 minus W2. Now weigh the beaker along with the water. Let its weight be M2. The weight of the water that overflowed is equal to M2 minus M1. It is found that W1 minus W2 is equal to M2 minus M1. Since the water that overflowed is actually the water displaced by the immersed sphere, we can conclude that the weight of the water displaced is equal to the upthrust or the apparent loss of weight of the immersed sphere. This verifies Archimedes' principle.
If you try to lift a weight from a swimming pool and then try to lift the same weight from the edge of the pool, you will notice that it feels heavier when it is out of the water. This was supposed to have been first explained by the Greek scientist Archimedes. He said that the water exerts an upward force or upthrust on any object in it. When you weigh an object in the air and then in water, the difference between the two readings show the upthrust, which is often called the loss in weight of the object. All liquids and gases are known as fluids. A fluid exerts an upward force when an object is immersed in it partially or wholly. This property is called upthrust or buoyancy. It is denoted by Fb. Upthrust can be greater than, equal to, or less than the weight W of the body. This upthrust determines whether the body floats or sinks in a fluid. If Fb is greater than W or Fb is equal to W, then the body will float. But if Fb is less than W, then the body will sink. Upthrust, being a force, is measured in Newton, N. Lifting a bucket of water from a well, pulling a fish out of water, and a body weighing less in the air than in vacuum are examples of the effects of upthrust. Let's look at the properties of upthrust. The larger the volume of the body submerged in liquid, the greater is the upthrust. The more the density of the liquid, the greater is the upthrust. You must have observed that when you put an empty can with the lid on into water, it floats. This is due to the upthrust in the water, since the volume of the can is more. Similarly, if a bunch of feathers and a stone of the same mass are allowed to fall through the air, the stone comes down faster than the bunch of feathers. The reason is that the upthrust due to the air on the bunch of feathers is greater than that on the stone, because the volume of the feathers is more than that of the stone. If you push identical pieces of cork into two different liquids, say water and glycerine, you will notice that your fingers experience more upthrust in glycerine as it has more density than water. The upthrust due to a liquid on a body depends on the volume of the body and the density of the liquid. The upthrust is equal to the product of the volume V of the body submerged in the liquid, the density ρ of the liquid, and the acceleration due to gravity g. Thus, FB is equal to V rho L G. You must have observed that if you drop a piece of iron into water, it sinks. This is because the force of gravity is greater than that of upthrust. Take identical masses of iron and cork and place them on the surface of water. See what happens. The piece of iron sinks, while the cork floats on the water. This is because the density of iron is greater than that of water. Now you know that if rho is greater than rho L, then the body sinks into the liquid. If rho is less than rho L, or if rho is equal to rho L, then the body floats on the liquid surface. Do you know why fluids exert an upthrust? When the amount of pressure that acts at a certain point in the liquid from all directions is equal, it causes an upthrust. When a block is immersed in a liquid, pressure acts on the lower part of the block, which is greater than that action on the upper part. Thus, the difference in the pressure between the two parts of the block causes the liquid to exert an upward force on the body. This is upthrust.
So we are going swimming?
Yes, let's wait for the pool to get free.
Ouch!
Haha! Did you know that Archimedes, a Greek scientist, went through a similar experience? While most of us have heard the story where Archimedes ran through the streets yelling, "Eureka!" the real problem he was struggling with at that time is not so well known. According to a famous Roman writer, a new crown had been made for King Hiero II, and Archimedes had to determine whether it was of pure gold. The king wanted reassurance that no silver had been added to the crown by a dishonest goldsmith. To do this, Archimedes needed to find a method to determine the volume of an object with an irregular shape. In this lesson, you will learn how Archimedes solved this problem and propounded the Archimedes Principle. You will also learn about buoyancy and flotation of objects. At the end of this lesson, you will be able to explain Archimedes' Principle and its applications, define relative density, explain the applications of relative density, apply the formula of relative density to calculate the density of a given substance, define buoyancy, and explain the phenomenon of flotation and sinking using the concept of buoyancy.
So, how did Archimedes solve the problem? And what did water have to do with it?
While taking a bath, Archimedes noticed that the level of water in his tub rose as he got in. He realized that he could use this effect to determine the volume of the king's crown. The submerged crown would displace an amount of water equal to its own volume. Based on this, he eventually propounded the Archimedes Principle. This principle states that when a body is immersed completely or partially in a fluid, it experiences an upward force that is equal to the weight of the fluid displaced by it. We can verify Archimedes' principle through an experiment. From a spring balance, Suspend a small block of iron weighing W1, say 700 grams. Take an overflow jar and fill it with water until it is on the verge of overflowing. Under the spout of the overflow jar, place an empty beaker that weighs W2, say 150 grams. Gently lower the iron block suspended from the spring balance into the overflow jar till the block is completely immersed in water. The water overflows into the empty beaker placed under the spout of the overflow jar. Now, note the weight of the iron block in water as well as the beaker with the displaced water. The weight of the iron block in water, say W3, is 600 grams. The weight of the beaker, say W4, is 250 grams. Thus, there is an apparent loss in the weight of the iron block. The apparent loss of weight of the block is equal to W1 minus W3. This is equal to 100 grams. The weight of the water displaced is equal to W4 minus W2. This equals 100 grams. You can see that W1 minus W3 is equal to W4 minus W2. Thus, this verifies that the difference of weight of the iron block inside and outside the water is equal to the weight of water displaced into the beaker.
So, once Archimedes had determined the volume of the crown, he could find out whether or not it was made of pure gold.
That's right. Remember, mass of an object is a product of density and volume. So, knowing the density of gold and the volume of the crown, Archimedes could perform the necessary calculations to solve the problem. The Archimedes Principle finds many applications in our lives. One of these applications is determining the density of a given liquid using an instrument called a hydrometer. A hydrometer is generally made of glass. It consists of a cylindrical stem and a bulb. The bulb contains a mercury or lead shot to make it heavy. This ensures that the hydrometer floats upright in a liquid. To determine the density of a liquid, it is poured into a tall jar, and a hydrometer is lowered gently into the jar to float freely on the liquid. The hydrometer reading gives the density of the liquid. For example, if we place the hydrometer in a jar of carbon tetrachloride, the hydrometer shows a reading of 1.6. Thus, the density of carbon tetrachloride is 1.6 gram per centimeter cube. As you know, the density of a substance is the mass of a unit volume of that substance. The density of a given substance under specified conditions remains the same and is one of its characteristic properties. However, sometimes it is more convenient to use another measure called relative density. The relative density of a substance is typically referred to as the ratio of density of the substance to the density of water. It indicates how heavy or light that substance is when compared to water. For laypersons, the concept of relative density may be easier to understand than density. For example, if we state the density of iridium as 22,650 kg per meter cube, not everyone may easily grasp how heavy iridium really is. However, if we say iridium is over 22 times as dense as water, the number gives us a realistic idea of weight of the unit volume of iridium. As a more common example, the relative density of silver is 10.5. This means silver is 10.5 times as heavy as water. Since the relative density is a ratio of similar quantities, it has no unit. However, while calculating the relative density of a substance, care should be taken that densities of the substance and water are expressed in the same system of units. The concept of relative density finds many applications, especially calculation of the densities of given liquids. For example, a lactometer is used to test the purity of milk on the basis of its relative density. An alcohol meter uses the concept of relative density to determine the alcoholic strength of a liquid. Similarly, a saccharometer is used in determining the amount of sugar in a solution. The formula for relative density of a given substance is: relative density is equal to density of a substance divided by density of water. Given the relative density of a substance, you can use this formula to determine the density of that substance. For example, the relative density of carbon tetrachloride is 1.6. To calculate its density, let's substitute the given values in the formula. Relative density of carbon tetrachloride is equal to density of carbon tetrachloride divided by density of water. 1.6 is equal to density of carbon tetrachloride divided by 1 gram per cubic centimeter. Density of carbon tetrachloride is equal to 1.6 into 1 gram per cubic centimeter. Therefore, the density of carbon tetrachloride in CGS system is equal to 1.6 gram per cubic centimeter. Now let's look at another aspect of Archimedes Principle, which explains the concept of floating and sinking, also known as buoyancy. As Archimedes' Principle mentions, when a body is immersed completely or partially in a fluid, it experiences an upward force. The upward force exerted by a fluid on any object is called upthrust, the buoyant force, or simply buoyancy. The concept of buoyancy explains why certain objects float on water while others sink. All objects experience buoyant force when immersed in water. Floating and sinking of objects depends on how the density of the object compares with the density of water. An experiment will help illustrate this concept. First, we take a beaker filled with water. Find two identical coins, one of metal and the other of plastic. Place both the coins on the surface of the water. The density of water is 1 gram per cubic centimeter. The density of iron is 7 gram per cubic centimeter. The density of plastic is 0.8 gram per cubic centimeter. The plastic coin floats and the metal coin sinks.
So how can we determine whether the buoyant force on an object will exceed its weight?
The magnitude of this buoyant force depends on the density of the fluid. Therefore, the floating and sinking of objects depends on how the density of the object compares with the density of water. The plastic coin floats in water because the density of the plastic coin is less than the density of water. Therefore, the upthrust of water on the plastic coin is greater than the net weight of the coin. On the other hand, the iron coin sinks because the density of the iron coin is higher than the density of water. Therefore, the upthrust of water on the metal coin is not able to overcome the net weight of the coin. Thus, according to the principle of buoyancy, objects with a density less than that of a given liquid float on that liquid. Objects with a density greater than a given liquid sink when placed in that liquid.
That's cool. But wait a minute. the density of iron is greater than that of water. So how is it that if we drop a piece of iron in water, it sinks? But our ships are built of iron and steel parts, and they don't seem to have any problem staying afloat in water.
That's a good question. To better understand why a ship floats, let's look at a very simple everyday example of buoyancy. Take an empty glass bottle and close its cap airtight. Put the bottle in a bucket filled with water. Then try to immerse the bottle in water. You'll observe that attempts to push the bottle down in the bucket are unsuccessful, and the bottle floats on water, even though the density of glass is higher than that of water. Here's the reason why. The bottle contains air inside it. The volume of the bottle includes the volume of air in it. The density of air is much less than that of water. This means that the overall density of the bottle becomes lower than that of water. Hence, the upthrust on the bottle is greater than the weight of the bottle. Due to this, the empty airtight bottle is pushed upward when we try to immerse it completely in water. Therefore, the glass bottle floats on water. In order to make the bottle immerse completely in water, the volume of water equivalent to that of the bottle must be displaced. Note, to keep the bottle completely immersed, the upward force on the bottle due to water must be balanced. This can be achieved by an externally applied force acting downwards. This force must at least be equal to the difference between the upward force and the weight of the bottle. The reason for flotation of the ship is similar to that of the flotation of the glass bottle. Even though the density of iron is more than that of water, the ship does not sink. The total volume of the ship includes the volume of the air in it and the volume of the metal. This reduces the overall density of the ship to a value much less than the density of water. Hence, the ship does not sink. The gravitational attractive force acting on a body is called its weight. If the mass of the body is equal to m, then its weight W is equal to mg, where g is the acceleration due to gravity. The weight of a body acts vertically downward through its center of gravity. When a body is immersed in a fluid, the fluid exerts an upward force on the body, known as the force of buoyancy or upthrust, Fb. According to Archimedes Principle, the force of buoyancy is equal to the weight of the fluid displaced. This force of buoyancy acts vertically upward through a point known as the center of buoyancy. The center of buoyancy is the center of gravity of the displaced fluid. If the body is completely immersed in the fluid, then its center of gravity coincides with the center of buoyancy. Whether the body immersed in a liquid sinks or floats depends on the magnitudes of the two forces acting on it. Now, consider a body of volume V and density ρb completely immersed in a liquid of density ρl. We know that the weight of the body is equal to mass of the body into acceleration due to gravity g. We also know that the mass of the body is equal to volume of the body V into its density rho b. Hence, the weight of the body W is equal to V into rho b into g. If the weight of the body W is greater than the force of buoyancy acting on it, Fb, then the body will sink in the liquid. In that case, the apparent weight of the body is equal to W minus Fb. Since the body is completely immersed in the liquid, the volume of the liquid displaced is equal to the volume of the body V. The force of buoyancy acting on the body, which is the weight of the liquid displaced, is equal to V into rho L into g. Since weight of the body is greater than the force of the buoyancy acting on the body, the density of the body sinking in the liquid is greater than the density of the liquid. In another case, if the weight of the body immersed in the liquid is equal to the force of the buoyancy acting on it, then the body will float just inside the liquid surface. In such a case, the apparent weight of the body is 0, and the density of the body is equal to the density of the liquid. When a body, such as cork, is placed in a liquid, it floats such that a part of it submerges in the liquid, and part floats above the liquid surface. When such a body is completely immersed in the liquid, its weight is less than the weight of the liquid displaced. It means that the weight of the body is less than the force of buoyancy acting on it when immersed in the liquid completely. Left alone, such bodies float on the liquid surface. This happens when the density of the body is less than the density of the liquid. When the body floats with its volume partially above the liquid surface, the volume of the liquid displaced by the body is equal to the volume of the submerged portion of the body. Since the body is in equilibrium, the force of buoyancy acting on the body must be equal to its weight. This is known as the law of flotation. The laws of flotation can be stated as: the weight of a floating body is equal to the weight of the liquid displaced. The center of gravity of a floating body and the center of buoyancy are in the same vertical line. Let us now derive a mathematical expression for the laws of flotation. Consider a cylindrical body with height h1 and cross-sectional area A, floating in a liquid to a depth of h2. Let rho b be the density of the body and rho L be the density of the liquid. Then, volume of the cylinder V is equal to A into H1, and volume of the liquid displaced VI is equal to A into H2. The mass of the cylinder M is equal to the product of its volume and density. Therefore, M is equal to V into rho B, which is equal to AH1 rho B. Weight of cylinder W is equal to mg, which is equal to AH1 rho bg. Let this be equation 1. Similarly, mass of the liquid displaced is equal to volume of the liquid displaced into density of the liquid, which is equal to VI into rho L. This is also equal to AH2 rho L. Therefore, the weight of the liquid displaced is equal to AH2 rho Lg. Let this be equation 2. However, according to the laws of flotation, for a floating body, the weight of a body is equal to the weight of the liquid displaced. From equations 1 and 2, we can write that AH1 rho bg is equal to AH2 rho Lg. This can also be written as H1 rho B is equal to H2 rho L. In terms of volumes, this equation can be written as V rho B is equal to VI rho L. Let us now discuss the different types of equilibrium states of a floating body. There are three types of equilibrium states: stable equilibrium, unstable equilibrium, and neutral equilibrium. A floating body is said to be in a stable equilibrium if the body returns to its original position after a small angular displacement. If the floating body overturns after a small angular displacement, then it is said to be in unstable equilibrium. After a small angular displacement, if the body settles at a new position without overturning, then it is said to be in neutral equilibrium. Let us observe the equilibrium conditions for a partially submerged body. Let G represent the center of gravity and B represent the center of buoyancy. For a stationary floating body, they lie on a vertical line. When a floating body is provided with a small angular displacement, the shape of the immersed volume changes. This changes the position of the center of buoyancy. Let the new position of the center of buoyancy be B'. The vertical line passing through point B' is the new line of action of the force of buoyancy. The point of intersection of the vertical line passing through the new center of buoyancy B' and the straight line passing through the center of gravity and the original center of buoyancy B is called the meta-center. Let us denote this point by M. The nature of equilibrium of a floating body depends on the position of the meta-center with respect to the center of gravity. If the center of gravity of the body lies below the meta-center, then the body will be in stable equilibrium. In this case, if the body is displaced in the anti-clockwise direction, then the moment of couples set by the two forces, weight and force of buoyancy, acts in the clockwise direction and brings the body back to its original position. Now consider a body which is heavily loaded at the top. When tilted slightly, the meta-center may lie below the center of gravity, and the floating body is in unstable equilibrium. In such a situation, if the body is displaced in the anti-clockwise direction, the moment of couples set up by the two forces, weight and upthrust, also tries to rotate the body in the anti-clockwise direction. This causes the body to overturn. The body is in neutral equilibrium if the center of gravity coincides with the meta-center. In such a situation, there will be no torque acting on the body. Let us now look at some applications of the laws of flotation. When a small iron nail sinks in water, how is a huge ship able to float? An iron nail sinks because it has more weight than the weight of the water it displaces. In other words, the density of the iron nail is greater than the density of water. In case of a ship, a large portion of it is hollow inside. This reduces the apparent density of the ship to a value less than the density of water. The weight of the water displaced by the ship is much more than its own weight. This makes the ship float on water. When loaded with more cargo, the weight of the ship increases, and hence it sinks further. The water in different seas have different densities. Therefore, when the ship sails from sea water of high density to sea water of low density, it sinks more. Considering this, the hull of a ship is marked with white lines all along its length. These lines are called plimsoll lines. Plimsoll lines indicate the safe limit for loading a ship in water of a particular density. if the ship is not sufficiently loaded, it can overturn in a rough sea. This is because, in such a situation, the ship's center of gravity tends to be higher than the meta center. As a consequence, the ship will be in unstable equilibrium. To avoid such a situation, ships are filled with ballast, which is heavy waste material, before they are allowed to sail out. The ballast lowers the center of gravity to below the meta center. Hence, the ship is in stable equilibrium. Let us now study the flotation of fish. Most fish have an organ known as the swim bladder. When they want to rise, fish release gas into the swim bladder and increase their volume. As a result, they displace more water. The force of buoyancy acting on them increases. To come down, a fish empties the bladder to the required extent, reducing the volume and the force of buoyancy acting on it. The working of a submarine is based on the flotation of fish. A submarine can dive into the water or rise to the surface as needed. The most important compartments of a submarine that help in its flotation are the ballast tank and the compressed air tank. To dive, the ballast tanks are filled with water so that the average density of the submarine becomes greater than the density of sea water, and the submarine dives. To rise, the water from the ballast tanks is forced out into the sea by allowing air from the compressed air tank to enter the ballast tank. As a result, the average density of the submarine decreases and the submarine rises. Let us now study the flotation of icebergs. The density of ice is less than the density of water. Therefore, huge masses of ice, known as icebergs, float in water. The part of the iceberg that appears on the water surface is very small. A large part of it is inside the water. Let V be the total volume of the iceberg and V' be the volume of the iceberg submerged in the water. According to the laws of flotation, the weight of the iceberg is equal to the weight of the seawater displaced by it. V into di into g is equal to V' into dw into g. Or V' by V is equal to di by dw. Here, di is the density of the iceberg and dw is the density of the seawater. Since most part of the iceberg is submerged in seawater, ships can hit the underwater ice and get sinked. Hence, icebergs are very dangerous.
When you throw a wooden cork in air, it falls to the ground due to gravity. But when you try to immerse the same cork in water, it bounces up because of an upward force acting on it. You can even feel this force with your hands. This upward force is known as upthrust or buoyant force. The principle of flotation states that when an object placed in a liquid displaces a weight of the liquid equal to its own weight, then it floats. In this case, the upthrust by the liquid on the object is equal to the weight of the object. an object in water appears to lose its weight. The apparent weight of the object can be written as actual weight of the object minus upthrust. As we know that the actual weight and upthrust are equal for floating objects, then the apparent weight of a floating object is equal to 0, or it appears to have no weight. Let us now verify the principle of flotation with the help of an experiment. Take a measuring cylinder and fill it with water up to 3/4 of its height. Note the level of water. Let its initial volume be V1 centimeter cube. Next, place an empty test tube in the water in the measuring cylinder. Now, place some lead shots in the test tube till it floats in a vertical position. Note the level of water in the cylinder. Let this final volume V2 centimeter cube. The difference between the water levels can be written as V2 minus V1 centimeter cube. This difference gives the volume of the water displaced by the test tube. Let us now find the weight of the displaced water. The weight of the displaced water can be written as V2 minus V1 into rho into g Newton, where rho is the density of water and g is the acceleration due to gravity. We know that the density of water, or rho, is equal to 1 gram per centimeter cube. Hence, the weight of the displaced water is equal to V2 minus V1 into g Newton. Now, take out the test tube and wipe it dry using tissue paper. Next, weigh the test tube along with the lead shots and note the reading. Let this weight be W. You will find that W is equal to V2 minus V1 into G, that is, the weight of the test tube while floating is equal to the weight of the water displaced by it. Thus, the principle of flotation is verified. Before conducting the experiment, let us recall Archimedes' principle. The principle states that the weight of water displaced by a body immersed partially or completely in it is equal to the apparent loss of the weight of the body. Let us now perform an experiment. Consider two cases for this experiment. First, the solid is heavier than water. Second, the solid is lighter than water. Let us start with the first case. Take a solid such as a metal sphere that is heavier than water and measure its weight in air using a spring balance. Let the weight of the metal sphere in air be W1 gram force. Now take a vessel and fill it with water up to the brim. Then slowly lower the metal sphere with a thread into the water till it is completely immersed. Ensure that the metal sphere does not touch the sides of the vessel. Also check that no air bubbles are trapped on the surface of the immersed sphere. Note the weight of the metal sphere. Let it be W2 gram force. You will observe that there is some loss of weight. This loss of weight of the metal sphere in water is equal to W1 minus W2 gram force. According to Archimedes Principle, the loss of weight of a metal sphere in water is equal to the weight of the water displaced by it. Hence, the weight of the water displaced by the metal sphere is equal to W1 minus W2 gram force. We know that the relative density of a metal sphere is equal to the weight of the metal sphere in air upon the weight of water displaced by the metal sphere, or the weight of the metal sphere in air upon the loss of weight of the metal sphere in water. By substituting the related values, we get the relative density of the metal sphere as W1 upon W1 minus W2. If any solid is soluble in water, we should take another liquid where the solid is insoluble and sinks. For such solids, relative density is equal to weight of the solid in air upon loss of weight of the solid in the liquid into relative density of the liquid. Next, let us find the relative density of a solid that is lighter than water, such as a cork. For this, let us take a sinker, such as a piece of metal or stone. Now, take a vessel and fill it with water to the brim. Suspend the sinker with a thread into the vessel such that it is completely immersed in water. Now measure the weight of the sinker. Let it be W1 gram force. Then tie a cork at the middle of the thread and measure the weight of the cork in air along with the sinker in water. Let it be W2 gram force. Next, tie the cork near to the sinker and immerse them in water. Measure the combined weight of the cork and the sinker in water. Let it be W3 gram force. You will notice that the combined weight of the sinker and the cork in water is less than the individual weight of the sinker in water. This is because the upthrust on the cork is more than the weight of the cork. Thus, the weight of the sinker in water is equal to W1 gram force. The weight of the sinker in water and cork in air is equal to W2 gram force, and the weight of the sinker and cork together in water is equal to W3 gram force. Based on these readings, we get that weight of the cork in air is equal to W2 minus W1 gram force, and the weight of the cork in water is equal to W3 minus W1 gram force. The loss in weight of the cork in water is equal to the weight of the cork in air minus weight of the cork in water. It can be written as W2 minus W1 minus W3 minus W1. By solving the equation, we get W2 minus W3 gram force. We also know that the relative density of the cork is equal to the weight of the cork in air upon the loss in the weight of the cork in water. By substituting all, the relative density of the cork becomes W2 minus W1 upon W2 minus W3. Using this formula, we can calculate the relative density of a solid that is lighter than water. Thus, we have deduced the formulae for the determination of the relative density of solids that are either heavier or lighter than water.
Can you distinguish between pure milk and milk adulterated with water? Yes, you can do this with the help of a device known as the lactometer. In fact, a lactometer is a specialized hydrometer used for checking the purity of milk. The hydrometer is an instrument used to find the relative density or specific gravity of liquids. It works on the law of flotation. A simple hydrometer constructed in the laboratory can be used to study its principle of working. Now, let us look at the construction of a simple hydrometer. Take a thin-walled flat-bottom test tube of cross-sectional area A. Fit a scale graduated in millimeters with the zero mark at the bottom inside the tube. Put some lead shots in the tube. This test tube works as a simple hydrometer. How can it be used to find the specific gravity of a liquid? Let's see. Place the test tube in a jar filled with water and adjust the number of lead shots so that the test tube floats vertically. Measure the length LW of the test tube inside the water. The volume of water displaced, VW, is equal to A into LW. If dW is the density of water and G is the acceleration due to gravity, then the weight of the water displaced is equal to VW into dW into G. This is also equal to A into LW into dW into G. According to the law of flotation, the weight of the floating test tube is equal to the weight of the water displaced. This is equal to A into LW into dW into G. Let this be equation 1. Now, place the test tube in another jar filled with a liquid of density dl and note the length of the test tube inside the liquid. Let it be LL. Then, the volume of the liquid displaced VL is equal to A into LL. Therefore, the weight of the liquid displaced is equal to VL into DL into G. This is also equal to A into LL into DL into G. Again, according to the law of flotation, the weight of the floating test tube is equal to the weight of the liquid displaced. This is equal to A into LL into DL into G. Let this be equation 2. From equations 1 and 2, A into LW into DW into G is equal to A into LL into DL into G. This can be written as DL by DW is equal to LW by LL. However, DL by DW is equal to density of the liquid by density of water, which is equal to the relative density of the liquid. Hence, the relative density of the liquid is equal to LW by LL. The hydrometer can be calibrated as described below. First, the hydrometer is made to float freely in water in a jar. A point up to which the hydrometer is immersed in water is noted. Let this be M. Let the volume of the hydrometer immersed in water be V. Since density of water is 1 gram per cubic centimeter, the weight of water displaced is equal to V into 1. That is, V gram force. The hydrometer is now floated vertically in a liquid of density ρ. Mark a point N on the stem corresponding to the level of the liquid. Let the distance Mn be L. Weight of the liquid displaced is equal to V plus La into ρ. Since the same hydrometer is used, weight of the liquid displaced is equal to the weight of the water displaced. Hence, V plus La into ρ is equal to V. On simplification, we get that L is equal to V into 1 minus ρ by A into ρ. The distances for various values of ρ are calculated and the corresponding points are marked on the stem. There are many drawbacks with a simple hydrometer. Firstly, it is not sensitive and cannot be used to identify minor changes in densities. Secondly, it may sink when placed in very light liquids. It may also overturn when placed in dense liquids. Many of these drawbacks are rectified in the Common Hydrometer. A common hydrometer consists of 3 main parts. It has a small bulb at the bottom called the gravity bulb. The gravity bulb is filled with heavy lead or iron shots. This increases the weight of the hydrometer and lowers its center of gravity, which helps it to float vertically in a liquid. Above the gravity bulb is a large hollow bulb known as the flotation bulb. This bulb, because of its large size, can displace a large volume of liquid and provide the required force of buoyancy. At the top of the hydrometer, there is a long and narrow cylindrical stem. The graduations on the stem indicate the density or relative density of the liquid. Note that the scale on the stem will have its least value at the top and the greatest value at the bottom. When the hydrometer is immersed in a liquid, the weight of the liquid displaced is equal to the weight of the hydrometer. Since the weight of the hydrometer is constant, it sinks deeper in a less dense liquid and floats high in a more dense liquid. The mark corresponding to the liquid surface gives the density of that liquid. Now, let us learn more about the lactometer. The relative density of pure milk is 1.03. The density decreases when milk is adulterated with water. Since the variation in the density of milk is very small, the lactometer must be highly sensitive. Most commercially available lactometers have 5 prominent markings. W, m by 4, m by 2, 3m by 4 and m. When placed in water, the lactometer dips to the level W. The lactometer dips to the level m by 4 if the sample contains only 25% milk. Similarly, m by 2 corresponds to 50% milk, 3m by 4 to 75% milk, and m corresponds to pure milk. It is important to note that if the milk is skimmed, then the lactometer cannot detect its purity. This is because once the lighter fat particles are removed from milk, its density increases. Another hydrometer that is specially used to check the concentration of sulfuric acid in an acid battery is known as an acid battery hydrometer. Acid batteries are used in cars and other vehicles. The electrolyte used in an acid battery is sulfuric acid of density 1250 to 1300 kilograms per meter cube. The density of the acid decreases as the battery discharges. The battery is not useful if the density becomes less than 1120 to 1160 kg per meter cube. Hence, it is very important to check the density of the sulfuric acid in a battery at regular intervals. An acid battery hydrometer consists of a small hydrometer with a short stem and a heavy gravity bulb. The graduations on the stem are marked from 1100 kg per meter cube to 1300 kg per meter cube. This hydrometer is placed in a cylindrical glass tube provided with a nozzle at one end and a rubber bulb at the other. Whenever the density of sulfuric acid is to be measured, the nozzle is dipped into the battery and the acid is sucked into the glass tube by squeezing and releasing the rubber bulb. The hydrometer starts floating in the acid and indicates its density. After noting the reading, the acid can be put back into the battery by squeezing the rubber bulb again. All the hydrometers you studied so far are of variable immersion hydrometers. Another type of hydrometer is the constant immersion hydrometer. Nicholson's hydrometer is an example of this type. It is made to immerse up to a mark on the stem. It is first placed in water and small weights are loaded on the platform until the water level reaches the mark on the wire stem. The device is then placed in a liquid of unknown relative density, and weights are added to the hydrometer so that the liquid level coincides with the same mark. The unknown relative density of the liquid can then be obtained in terms of the mass of the hydrometer and the two sets of masses used to bring it to the reference line.